Welcome. This question says a spring and block system oscillates with simple harmonic motion. 4 kilogram block is displaced 2 meters from the equilibrium position and released at time t equals 0. The system has an angular frequency of 5 radians per second. What is the instantaneous kinetic energy of the system at 1.3 seconds? So let's picture this thing. So here's the table, and we have our spring, and here's our mass, and then there's an equilibrium position somewhere in here, and we start off at the right extreme, and we happen to be 2 meters to the right, and we let the system go, and the system oscillates with simple harmonic motion. So this is time pointing downwards. This is my x-axis going horizontally in this case, and at some point t equals was it 1.3 seconds. So if I look here, I can kind of picture that 1.3 might be somewhere like, oh, I don't know, somewhere here, for example. That could be 1.3 seconds, and then we want to know what the kinetic energy of the particle is at this point. Well, it's got a combination, hasn't it? It's got a little bit of spring potential and it's got some kinetic energy, and the combination of those is the total mechanical energy. And because it's an isolated system, there's no friction involved. The mechanical energy is constant throughout this process. So at different points on here, it would have different amounts of kinetic energy and different amounts of spring potential energy. So what do we know? Let's make a list of what we know. And what we know from the writing is that the mass of the system is equal to 4 kilograms. And we know that the maximum displacement is the same. Of course, it's the amplitude, which is 2 meters. And we know that because we moved it 2 meters to the right and then we let it go. We didn't throw it further, we let it go. And so it's never going to be more than 2 meters away from the equilibrium position, and so our amplitude is 2 meters. And then we have the frequency is given in angular terms, and it's 5 radians per second. And just to put that in perspective, if it was 2 pi radians per second, then that means it would have a frequency of about 1 hertz, because 2 pi radians is about 1 complete circle, and that's 1 wavelength, or one oscillation. So it's 5 radians per second, so it's going a little bit slower than that. So it's going to take slightly more than 1 second to go through one oscillation. And then it says, what is the instantaneous kinetic energy? So we want to find my kinetic energy at a time 1.3 seconds. And I can use a bit of shorthand here and say K of 1.3, and that sort of reminds me I'm talking about the kinetic energy at 1.3 seconds. I need to come up with a relationship for instantaneous kinetic energy, and my instantaneous kinetic energy is going to equal 1/2, and then it's going to be m omega squared a squared, and then sine squared omega t. And that looks complicated, but let's try and make it a bit more accessible. So let's remind ourselves of a few things. You know, we learned pretty early on that for a particle, kinetic energy is 1/2 mv squared for just a particle translating, moving through space is 1/2 mv squared. And of course the dimensions of that is going to be, well, mass times length squared over time squared. So let's at least check and see if this system has the same kind of dimensions. Well, the 1/2 is there, well, that's dimensionless, but if I look at this, I have a mass, and then I have an omega. An omega is in radians per second, A radian is dimensionless. So there's no dimensions on top, but there is time on the bottom. So that would be t, and it is omega squared, so that would be t squared. And then we have the amplitude. And amplitude, of course, is the length, and the length is squared. So that first bit has the same dimensions as we're expecting. And then this sine squared omega t, well, a sine or a sine squared is just a factor which goes from 0 to 1 as the time changes. So that's just a scaling factor. So this, although, you know, I think in the end you have to learn it. I think that if you learn it, it just makes a lot of sense. If you go beyond learning just a sequence of letters and not giving much thought to it, if you actually think through it and try to make sense of why it is the form that it is, it just makes a lot more sense. So we're going to say K is equal to 1/2, and my mass, well, my mass is 4, and my omega is 5, but that's got to be squared. And my amplitude is 2, but that's got to be squared. And then my sine squared of omega t, omega is 5 times t is 1.3. So then let's just do a little bit more on this. So this is going to be 1/2 times 4 times 25 times 4 times sine squared of 5 3s are 15, 6.5. That's 6.5 radians, of course. So then K is equal to, and I can go through this and say, well, 25 times 4 is 100, and 2 times 100 is 200. 200 sine squared 6.5. So then, getting my little calculator, first thing I do is I check I'm in radians, which I am, and I go sine of 6.5. Let's go 6.5, 6.5. Sorry, I'm all thumbs this afternoon. 6.5, and I get 0.215, and then I've got to square that because it's sine squared. I get 0.046, and then I multiply that by 200, and I get 9.255. So K, let's go back to here. So K, sorry, my pen's acting up. So K is equal to 9.255 joules. And when I look at my answers, 9.26 is there, so it's the answer at the bottom. So what do you think? It's a longer equation. At first glance it seems a little bit complicated, but there's some clues. The half is reminiscent of my old kinetic energy equation. The mass, of course, is there. And the rest of it is just a way of working out the velocity. And then working out a velocity, and then we have a scaling factor. So there we have it.